Hello, everybody. I'm Adnan Hamid. I'm your first demo speaker. One generally expects somebody from the conference to introduce me, and you know how it goes, right? But whatever, I'll just get going. I'm Adnan. I'm founder and CTO at Breker Verification Systems. This is a quick demo on the new RISC-V, well, not so new, RISC-V Advanced Interrupt Architecture, right? 80% of this talk is explaining what AIA is all about, and 20% is what we did to solve the problem. Okay, and I think I get about 10 minutes to talk. So the big idea in AIA is create a flexible way to route interrupts, especially in a big system, right, in a big SoC. And the key thing that is being done is give the SoC architect flexibility between using either wired interrupts, old-fashioned, the ones we're used to, right, where DMA says I'm done with something and there's actual physical wire that runs around to the CPU, versus a so-called message signaled interrupt. This is the idea that any agent that's trying to indicate that a system needs an interrupt will write to a well-known address with some extra info, and the data can be something useful for the interrupt handler. And now you don't have to have this extra sideband wire. You can transfer that right on the main fabric. And it allows for delegation of interrupts, just like the RISC-V interrupts let you delegate. So you can say, okay, interrupt came in. Do I want to treat it in the most secure stage, or it's not a secure interrupt? Send it back to supervised mode or something like that. Okay. Now, hello. Now, like most the RISC-V specifications, if you open up the spec and try to understand what the heck it's telling you, I at least find it completely impenetrable, right? It's like, it gives you a lot of words. It's actually not that complicated, but it takes a while to untangle that it's not complicated, okay? And the basic idea is this. If you're implementing AIA, again, every piece, like in RISC-V, everything is optional, but if you're doing the message signal interrupts, every CPU gets something called an IMSIC, an incoming message signaled interrupt controller, okay? IMSIC. And all this is basically giving each CPU a little piece of logic that is a set of MMIO registers, right? They're basically registers somewhere in the memory space. They're well advertised, so the system architect, the system software knows that the registers for CPU 0 are at address 1000, 1 is at 2000, so they're well advertised addresses. So that's the block. Within the block, you get separate register files for each privilege level. So there's an M mode privilege level, S mode, virtual user mode, and so on. Okay. And the idea is, depending on who you're trying to interrupt, right? If you're a DMA or if RMMU, by each of, do I have a laser thing? Each of those files have well-known addresses, and you're going to write to the correct file at the correct location to say, okay, S mode, I want to send you interrupt 53 with this minor ID. There's a special number you can send that lets you give more information than you could when there was a wire. Okay, so this is, once you're going to untangle what it's trying to say, it's a pretty good idea. Okay. That's one piece of it. The other piece of it is a so-called APLIC, right? The Advanced Platform Level Interrupt Controller, okay? I feel like I'm teaching ABC, okay. And this is the guy who is outside the core, downstream of the fabric, dealing with all the system interrupts coming in, right? So he wants to talk to internal and external sources of interrupts, right? So your on-chip DMA has an interrupt, it'll go to the APLIC, right? Because he's probably doing the DMA is not smart, right? You don't want to go fix him to do the MSI message. You just send an interrupt, APLIC deals with it. And then the APLIC itself can be designed and configured to either send wired interrupts into the CPUs or send this MSI interrupts, right? These message-based interrupts, depending on how you want to design it. So a lot of flexibility on the system architect's part. So how do all these pieces get used? All right, what's the basic idea? So one simple use case is interprocessor interrupts. Okay, so the Clint, the core level interrupt controller, gives us a mechanism to do interprocessor interrupts. There's special addresses you can write to interrupt other cores. This is a fancier way of doing the same thing, okay? Where one CPU can write to the interrupt file. Remember, the interrupt files are just addresses in memory, saying, hey, I want to send supervisor mode interrupt number 15, right? And with this minor ID. And it's a way to provide information along with the interrupt, okay? Because this is the big problem in interrupts, right? You not only want to do the interrupt, the guy receiving the interrupt needs to somehow interrogate you back to know why are you calling me? So you can send some information about why you're calling. PCIe may have been the ones to come up with MSI in the first place. I don't know. PCIe has this idea of message signal interrupts. I don't know if it was there before that or not. And that was, okay, we built this beautiful PCIe high performance interface. We need to communicate interrupts. We didn't want to send a new wire up that interface. So we said, oh, if we do a special write to a special address, this means an interrupt. This gave rise to the message signal interrupt. And the IMSIC is designed to receive those interrupts, right? So it works seamlessly with PCI Express. If you have your on-chip DMA, it'll send its wired interrupt to the APLIC. If you're receiving GPIO interrupts from the SoC, it'll go to the APLIC. And now the APLIC can make the APLIC architect can make some decision, right? He can say, okay, I'm going to gather these and I'm going to do a memory write into the IMSIC interrupt file. This is one way you could communicate. Or we could say, what am I doing? Or you can say, nope, I'm going to tell the CPU a dedicated wire that I have an interrupt for you, probably going to the CPU's Clint, right? So these are kind of the big ideas, the big different flows that you can do. Of course, it's hardware. Of course, it's RISC-V, so there are 5,000 variations of everything, but these are the big ideas. Okay. Okay. So diving a little bit more into this. Yeah, see, I'm giving a lecture on this after you taught it to me, huh? Okay. So for the IMSIC, right, the part that we put next to the CPU, the idea is we have one per heart, right? So it defines this memory mapped file at a well-known address. And you can interrupt the CPU by doing a write to the correct address. The advantage of this is you get to send that write across your NOC, right? You could have, 50 different agents in the system. The anyway reading and writing memory is just one more write. It's a beautiful thing. NOCs are usually high throughput, high performance. This is all good. The downside is if you're putting this write in with a bunch of other writes going on in the system, you have no reliability in your latency. Right? Sometimes it'll go fast, sometimes it'll be slow. It's not measurable. So folks who do real-time systems really hate this kind of stuff, and they want to push back towards no, do it with the wires, because it doesn't matter to me if it takes 10 cycles to communicate. I just need to know that it'll be exactly 10 cycles and not 11 and not 9. Okay. Okay, and as I showed you in the picture, right, there's separate files for each privilege level. This goes to security and delegation. Who can write to these M6? Anybody in the system who wants, right? Another CPU, interprocessor interrupts, on-core IPs like a DMA, PCI Express, the APLIC, anybody who wants to signal this interrupt. And the sort of information that is in the memory mapped in a file, right, is, okay, a global interrupt, right? If you turn that one off, nothing flows. Some threshold number, basically lower priority interrupts don't get communicated. You can read that file to see what pending interrupts are there. You can enable each of the interrupts. And in the end, it's not that scary. It's really hard to understand this stuff when you try to read the doc, but in the end, it's not that scary, okay? They're just many, many interrupts, and you have to know on this platform how many of them we implemented and where the addresses are and all this kind of jazz. Okay. The other half, the APLIC. This is the guy who receives all the wired interrupts from outside, from insides. He has extensive knowledge. He can be programmed to say, hey, who is going to receive this interrupt? Is it core 1 versus core 7? Is it going to go to supervisor mode? Is it going to go to M mode? Is it going to go to virtual mode, right? He can be configured to communicate via, that's hard to say, via wires or via messages, right? So again, architecture decisions. And he has a bigger memory mapped structure. He can do all kinds of delegation. And again, I'm trying to give you a flavor of the kind of information they put in these files. So there's a master enable for this. There's the delegation rules. There's information on the APLIC now needs to know where the M6 addresses are. Can you keep up with all those acronyms? So we got to tell him where it is. We have information about where each interrupt source should be routed to, and on and on. Okay. So what to do about this, right? So Breker is in the business of test suite synthesis. We are a general purpose system level test generator. We've been doing a lot of work for RISC-V specific test generation. We cover all your regular CPU level extensions, right, priv, unpriv, but we are also in the system level. And the general idea behind this flow is that there exists some system VIP, some pre-built model. This is the guy that has all the knowledge. It is fed into the synthesis tool. The synthesis tool spits out two things. One half is it spits out some C code with inline assembly. This is the part that runs the CPU. And the other half is this so-called TBX file that's read by a tool-specific component called the TREC box. It's essentially a transactor running in the test bench. And he can control all the IOs. So he can inject a PCIe MSI, or he can inject a wired interrupt. And the TREC box and the embedded program are communicating over a mailbox. So this is how we're coordinating what's happening on the inside with what's happening on the outside. Okay. So if we look into what a test would look like, you spin it up. The first thing we do is go off and configure all these, the AIA system, in other words, M6 and APLICs. I get so tongue twisted, to pick some random configuration for it, right? There are, as with everything, there are thousands, if not millions of different configurations you could go after, but pick one for this test. Then the test itself, we are predicting for the trap handler, hey, you expect this interrupt at this level with this minor ID. Then we go trigger the interrupt. In this case, we're doing an interprocessor interrupt where who's talking? Okay, so hard 0 is doing an interrupt to hard 3, sending in this minor ID of 1F, which is a random number, right? Then once we've done sending that, right, we're sitting there and waiting to see, hey, was the interrupt received by the right trap handler, right? So if the interrupt got lost, this guy will basically hang. Okay, he's basically waiting until he hears that the trap handler got the interrupt. And then we're checking that we got the right results. Meanwhile, there's a slew of other interrupts coming in from the other cores, right? So basically a storm of messages coming into this M6, create as much trouble as possible, try to get the hardware to fail. And of course, this is being crossed with every other type of instruction, every vector operation, every memory operation, and so on. And at the end of this, we're checking to make sure that there were no spurious interrupts, right? There are two things we're worried about. One, we didn't lose the interrupt we tried to send, and second, it didn't get sent more than once. So at the end of test, we're checking to make sure that there were no spurious interrupts in the flow. Overall, this stuff is tied to some debug infrastructure. So when you're looking at a test, it'll tell you, hey, this is the operation that failed. He'll tell you what memories were used by that. He'll give you the log message for the error. He'll tell you where in the code this error came from. So this is usually where we debug this stuff. Because waveforms, not so easy to debug this stuff, right? If you have 8 cores in play and 30 interrupts and only one of them failed, finding where it was in the test that failed is complicated, and this thing will tell you. We have this idea of coverage where we're thinking about, you know, those thousands, if not millions of possible configurations. Each of these paths through the graph are tracing the different combinations. The green paths are the ones that have been exercised. The red ones are waiting to go. So this is how we can check for large cross-coverage spaces. Have we done all the cases? And then, of course, in the end game, what's happening is we are linking the ISA spec to the Breker test plan, and the Breker test plan is tied to these cover points, and that's how we do the closure on the overall problem. Okay, that's it. Do I have any questions? 10,000-foot view? None. It's kind of like asking what's the difference between a RISC-V CPU and an ARM CPU. Okay, RISC-V says reduced instruction set. We only have 1,300 instructions. I don't know what the ARM instruction count is, but it's about that, right? So same idea, but redesigned, designed from scratch, different mechanics, but ARM has a distributed interrupt processing thing. So, and we service ARM designs as well, right? So same old, all different, right? Same but different. Okay. Yeah. What a great question. The question was, is AIA the same as Clint? Click and Clint, I think, might be synonyms. I'm not sure the difference between those two, okay? But both of either way, those are core level thought through at a cluster scope, whereas AIA is thought through at the system scope. But that's a big point, okay? Okay, cool. Who's up next? So, yeah. Verification is a search problem, and the search problem is searching all these crosses, and that's what this tool does really well. So absolutely. The complication in this is that the spec allows for so much flexibility on the system architecture that you have to take in a good deal of information. Did they implement wired interrupts? Did they implement only MSI interrupts? Do they still have the Clint in there? Or did they throw, you have a choice. Do you also do interprocessor interrupt with the Clint as well as MSI or not? You can decide. So there's some complexity to it, but yes, we do all of them. Whatever the system will support, we will do them.